All right, so this is suggested problem set 2.2 for AP Physics, and we are starting with problem number 3.11, talking about crickets chirpy, and we'll go with Mulata. They jump from the top of a vertical cliff. Chirpy drops straight downward and reaches the ground in 2.7 seconds, while Mulata jumps horizontally with an initial speed of 95 centimeters per second. So let's sketch this problem really quickly. So we have one cricket that goes straight down, and it takes 2.7 seconds to fall. So I'll even call that T-fall. And then the other cricket jumps horizontally with some initial speed of 95.0 centimeters per second. So we want to know how far from the base of the cliff this second cricket will hit the ground. So make some kind of parabolic path like this before hitting the ground. And we want to know this distance we'll call x. So the way we're going to go about solving this is we are going to start by using this time to fall to figure out how long Mulata will be in the air. So we can do very little math and solve this problem, right? We know, or we have to assume, that the crickets fall at the same rate, because everything has the same acceleration on Earth if we neglect air resistance. So they have the same, they have the same time in the air because they have the same acceleration. So the acceleration for Chirpy would be equal to the same acceleration for Mulata. So we can therefore say that x would just be equal to v in the x direction times some t. And so this x is just going to be the 95 centimeters per second multiplied by the 2.7 seconds. So the second cricket should fall and land about 256.5 centimeters from the base of the cliff. So always keep in mind small facts that allow you to do less math. The less math you do, the less opportunity you have to make a simple mistake. Now, number 3.12. So a quarterback throws a football with an initial upward velocity component of 12 meters per second and a horizontal velocity component of 20 meters per second. I'm going to start and just sketch this as two vectors. So we'll do an initial vertical velocity. So we'll say this is v naught y of 12 meters per second. And then an initial horizontal component of, or rather v naught x of 20 meters per second. And so ignoring air resistance, we want to know how much time is required for the football to reach the highest point of its trajectory. So we're first interested in time. So we have v naught y. And we want to use v naught y because we know that the time in the air is dependent only on the vertical component. And we know we're looking for time. We know at the peak of its trajectory, the y velocity will be 0. And we also know that throughout the course of this y motion, the acceleration would be equal to negative g, which we'll just call negative 10. So, which equation has all four of these things in it? Well, there's a few that we could use for this, but ideally we will just use the definition for average acceleration. So because this is constant acceleration, we know that the average acceleration is just going to be vy minus v naught y over the total time in the air. So we can rearrange this quite easily to see that time will be equal to vy minus v naught y over our acceleration. And again, we can do this because acceleration is constant. So if it's constant, then that must be equal to our average acceleration. So plugging in some values for this, we have vy is 0 minus our v naught y of 12 all over our average acceleration of 10. So we have a positive 1.2 seconds to reach the peak of our trajectory. Part B says, how high is this point? Now at this point we have some options. So we could just say that We could just go ahead and calculate how high it goes based off of the second kinematic equation. So we could go y equals y naught plus v naught yt plus 1/2 ayt squared based off of our time that we just calculated. So y0 or y naught is 0, and we are left with y equals, so substituting as well here, 12 times 1.2 plus 1/2 times -10, don't forget the negative, times 1.2 squared. So again, do not forget the negative here. Our vector acceleration has a sign, and we must include that sign if we are going to get a correct representation of the motion of this object. So if we plug this into our calculator, we get a y, or a final y, after 1.2 seconds of 7.2, and that should be meters as our velocity was given in meters per second. So C says, how much time after it's thrown is it required for the football to return to its original level? So thankfully, we really don't have to do any math for this, because we know that for an object thrown in free fall, we are going to have some symmetry to that object's motion. So however long it took for us to get to the peak, which in this case was 1.2 seconds, will be half of the time that it takes to get back to the same level. Therefore, the time that it takes to get back to the same level should just be 2.4 seconds. Now part D says, so actually, I guess we need to complete answer C. So this should be 2 times, right? So it should be 2 times the time from part A. Then we have for D, how far has the football traveled horizontally in this time? Thankfully, again, this is a very easy question. So all we have is the change in x position is going to be equal to our x velocity times t, because velocity in the x direction is constant, right? There's no acceleration in the x direction. So my x displacement will simply be 20 times the 2.4 seconds that were in the air. So the distance that the ball travels is quite simply 48 meters in the horizontal direction. Now, part E says to draw xt, yt, vxt, and vyt graphs for this motion. So, in the x direction, we're going to start at the origin, and we're going to move at a constant speed. So we should just have something that looks like a straight line with a positive slope. If we really want to label it, we could say that at the end of it, it has 48 meters in 2.4 seconds. Try not to go over the page here. In the y direction, we actually have a parabola. So we have an initial y velocity, and then we have a increasing rate of change. So we should have something that curves downward like this. Let's make that a little more exaggerated just for the sake of argument. So we have something that looks rather like this, where we end up with, we do not have an initial y height. So we should end up starting from the origin and making a parabolic shape like this, because we go up and then we come back down to the same height. Then, in our velocities, we have very easy Vx, which is just a constant positive velocity. And for our y direction, we have an initial positive y with a constant acceleration. So we should have something that looks like this. And if we want to be really, really specific, we can say that we would start at a positive 12, and we would end at a negative 12, and that's from symmetry. Right? And this, of course, also ends at 2.4 seconds. We can go back to the x velocity as well and say that this is positive 20. We could label the y and say that at the height, we have a height of 7.2 meters. You can be as specific as you want, but it is typically good to include values if you know them. So that's all there is for this question. It's mostly about making sure that you can use all the different little pieces that fit together for a question like this. All right, so question 3.13. During a storm, a car traveling on a level horizontal road comes upon a bridge that is washed out. The driver must get to the other side, so he decides to try leaping the river with his car. So I'm going to go ahead and start sketching this. So we have a car traveling on a horizontal road, and he gets to a gap where his side of the gap is 21.3 meters above the river. So this is not completely to scale, but it'll be fine. And the opposite side is only 1.8 meters above the river, so much lower. So 1.8 meters. The river itself is 48 meters wide, so the distance between these two sides is 48 meters. And we need to know how fast the car should be going in order to reach the other side just barely. So here's my car. Looks more like a Oscar Mayer Wienermobile, and it will make some kind of parabolic path like this. So how fast should it be traveling? Well, we know it's going to leave with some horizontal velocity, and we know that because it is traveling horizontally initially. So we'll have some v naught x that we don't know, and we'll have some v naught y that is 0. So how fast should it be going to get to the other side? Well, first we're going to figure out how much time it spends in the air. So the time that it spends in the air, so this is part A, the time that it spends in the air is our current goal, because we need to know how long it's in the air in order to figure out how fast it has to be traveling in order to get to the other side. So we know that our delta y comes from our y and y naught, so we'll do y minus y naught, where our y value, our final y, is 1.8 meters. Our initial y value is 21.3 meters. So we can say that our delta y is going to be 1.8 minus 21.3, or, with a little bit of calculator, negative 19.5 meters. Now you could alternatively just use y and y naught. And we also know that our acceleration in the y direction is negative g, or negative 10 meters per second squared. And we also know that v naught y is 0, as we just stated. So we can actually go straight to the second kinematic equation if we wanted to, and just start with y equals y naught plus v naught y times t plus 1/2 ay times the square of t. So we're actually going to be solving for time here, and since we're solving for time with some simplifications, it's not too bad. So we know that v naught y is 0, so this term is actually 0. And our y minus y naught is negative 19.5, or we can just go ahead and say or we can just go ahead and say, since y minus y naught is negative 19.5, that negative 19.5 is going to be equal to 1/2 times negative 10 times t squared. And so I'm going to be multiplying by 2 and dividing by negative 10 and square rooting that. So I have 2 times negative 19.5 over negative 10, all square rooted. And this tells us our time in the air is going to be 1.974 or 1.975 seconds. So I'm not going to round that as much as I can. So 1.975 sounds good. And so that's the amount of time that we have in the air. So the next part is, how fast should this car be going in order to get across 48 meters in this span of time? Well, I know that the distance in the x direction that I travel must be v naught x times t, as my horizontal velocity will not change at all. So if I want to solve this for my v naught x, I'm going to have delta x over t, which in this case is just going to be 48 meters over 1.975 seconds. So my initial x velocity, and therefore my initial speed, must be 24.3 meters per second. And that's the speed the car must be going as it leaves the side of the road. Part B says, what is the speed of the car just before it lands on the other side? So here, I already know that since my x direction does not change, that my x velocity is equal to my initial x velocity. The part that I don't know is my y velocity at this point. So Vy has to come from somewhere. So Vy will just come from a different equation. Now I can use either the first kinematic equation or the third kinematic equation. So I could use V equals V naught plus AT in the y direction. So all of these will get a y subscript. And I'll know that V naught y is 0. So this just becomes Vy equals negative 10 times t. And so with my 1.975 seconds, I know that Vy would be negative 10 times 1.975, which is just negative 19.75, and that's meters per second. And so to find my actual velocity, or rather my speed before I hit, then I'm going to need to use some trigonometry. So I have my x component and my y component, and you can treat this just as a triangle. So if you helps to think of here's Vy and here's now my triangle, then my actual V is just this third side. So this is my speed. The magnitude of this just comes from Pythagorean theorem. So the magnitude of my velocity will just be the square root of Vx squared plus Vy squared, or the square root of my Vx, which was found to be 24.3 squared, plus the square of my newly found y velocity, which is negative 19.75 squared. All of that square rooted. And so my speed, which is the magnitude of my velocity vector, is going to be, with a little calculator magic here, 31.3 approximately meters per second. Question 3.19. In a carnival booth, you can win a stuffed giraffe if you toss a quarter into a small dish. The dish is on the shelf above a point where the quarter leaves your hand and is a horizontal distance of 2.1 meters from that point. We toss with an initial velocity of 6.4 meters per second at an angle of 60 degrees above the horizontal. The coin will land in the dish if you do that. So, part A asks, what is the height of the shelf above the point where the quarter leaves your hand? So we are looking for this distance right here. This is part A. So, in order to do that, I want to know about the y direction. But in order to find the y direction in this case, I need to know how long my object is in the air. So I actually go through the x direction in order to do this. So because this is a two-dimensional problem, my first step really should be to find my components, which would be for the x direction, v times the cosine of 60 degrees, which for us is just going to be, so this will be 6.4 times the cosine of 60 degrees, which, making sure your calculator is in degrees, gives 3.2, and that's meters per second. This is our x direction. In the y direction, same thing, but we're going to use the sine of 60 degrees. And the reason for that is, if you go and look at your image here, this would be v naught y, and this would be v naught x. So the sine involves the opposite side, the opposite component in this case. So it'd be 6.4 times the sine of 60 degrees, which is going to be 5.54 meters per second. So first we'll find the time that my object is in the air. So we know from the x direction that our displacement in the x direction will be just v naught x times t. And so we will actually end up with just, if we solve for time, delta x over v naught x, which for us is going to be 2.1 meters over 3.2 meters per second. So the time that our object spends in the air has to be 0.65625. I'll just write, I can write it all. Seconds. So this is the time our object spends in the air. And now we want to use the second kinematic equation for the y direction in order to figure out its height at this time. So for the second kinematic equation in the y direction, I have y equals y naught plus v naught y plus 1/2 acceleration in the y direction times the square of time. And we can go ahead and just define that this is 0 height, right? So we can say that this is 0 height. I guess we'll say 0 meters. And from that point, we're only going up. So our y naught will end up being 0. That's the only simplification we're able to make. So I'm going to go ahead and say y. So I'm going to say that our final y is what we're looking for. So we have y equals, now v naught y is 6.4 times the sine of this angle, or as we found earlier, 5.54 meters per second, multiplied by our time of 0.65625 seconds, plus 1/2 times -10 times 0.65625 seconds squared. Do not forget the square. And if we go ahead and plug this into our calculator, we end up with positive 1.48 meters. And so that is the distance above where the quarter left my hand. So B says, what is the vertical component of the velocity of the quarter just before it lands in the dish? So we can actually go ahead and just use the first kinematic equation here. So Vy equals V naught y plus Ayt, with the fact that we know our V naught y to be 5.54. We know our y acceleration to be -10 or -9.8. And we know the time in the air to be 0.65625 seconds. So our y velocity just before it lands in the dish should be -1, and that's actually -1 to the 100th place, meters per second. And that's all there is to this problem. Question 3.20. Firemen use a high-pressure hose to shoot a stream of water at a burning building. The water has a speed of 25 meters per second as it leaves the end of the hose and then exhibits projectile motion. So, they adjust the angle of elevation alpha of the hose until the water takes 3 seconds to reach a building 45 meters away. So at this point, I'm going to go ahead and start drawing this. So here is my building, and that building is 45 meters away. And if we want, we can even draw the building on fire. Ooh, it's on fire. So the water leaves the hose with a speed of, so this is a V naught, of 25 meters per second at some angle alpha. And it takes 3 seconds to reach the building. So my water, whatever path it takes 3 seconds to reach the building. So we're going to go ahead and just write 3 seconds off to the side. And there is no air resistance. So we want to first off find alpha. Now the way that we do this is it's a two-dimensional problem. So I'm going to start by finding V naught x and V naught y. So it's going to be V naught times the cosine of alpha. Now all of a sudden I realize that I don't know alpha. So this is going to be a little tricky to solve at this point. All right. I do, however, have an alternative way that I could find V naught x. So I know that delta x is equal to Vx times t. And Vx in this case is actually going to be equal to V naught x because there is no horizontal acceleration. So I can find V naught x to be just my horizontal displacement over time, which is going to be 45 meters over 3 seconds, or 15 meters per second. So, knowing that v naught x is 15 meters per second, I can actually solve for the cosine of alpha, which would be v naught x over v naught. Therefore, my alpha is just the arc cosine of this ratio. So I can go ahead and put this in my calculator. So what I'm going to put in my calculator is going to be v naught x, which is 15, over v naught, which is 25. I'm going to find the arc cosine of this to find my angle. So that would be arc cosine of 15 over 25. It does not matter if you're in radians or degrees for this particular part. It just gives you a different output. So typically we would want degrees. And our value for alpha we get should be 53.1 degrees. So this is all part A. Part B says find the speed and acceleration of the water at the highest point of its trajectory. So part of this should be really easy, especially if you know anything about projectile motion. So the speed at the peak, as it describes it, or the highest point, is just going to be equal to our v naught x, because vy at the highest point is 0. So our speed at the highest point, so we can just say v, not v naught, or not in a kind of vector, is just going to be the 15 meters per second we found for v naught x. Our acceleration, now it does just say acceleration, should be in the negative y direction. So my acceleration as a vector is just going to be, we can see either negative g, or we can say negative 9.8 or negative 10. So let's just do 9.8 for once. Negative 9.8 in the j direction. Or we could say negative 9.8 in the y direction. And this is going to be meters per second, or meters per second squared. So part C says, how high above the ground does the water strike the building, and how fast is it moving just before it hits the building? So in order to figure out how high it hits the building, I can just use my second kinematic equation for the y direction. So y equals y naught plus v naught y times t plus 1/2 ay t squared. So one thing that's missing is we do not know v naught y at this instant. So we need to find v naught y. So v naught y is given to be v naught times the sine of alpha. So go ahead and calculate v naught y by doing 25 times the sine of the alpha we found, which is 53.1 degrees. And so v naught y will end up being, with that 53.1 degrees, about 20 meters per second. It's 19.99, so I'm going to go ahead and round that to 20. So my y naught I set as 0. So if you want to go back to my drawing, I'll set my origin to be right here. So this is my origin. So this is the positive x. This is the positive y direction, just to be clear with my axes. Then whatever height should end up being 20 times the 3 seconds that is given for the before the hose hits the building, plus 1/2 times negative, I'm going to go back to 10, I probably should have put negative 10 here for my acceleration, times the 3 seconds again that it's in the air. And so my y position for the water after 3 seconds should be 15 meters above the ground. Pardon me? 15 meters above the ground. Now the second part says calculate how fast it's moving just before it hits the building. So I know, again, we're going to be doing this trigonometry bit. So we have Vx in the y direction, or Vx in the x direction, and Vy, and we want to find the magnitude of this vector. So we end up with needing to know Vy at that point. So Vy will just come from V naught y plus At So Vy will end up being our positive y velocity, which we just found to be 20 meters per second, minus 10 times the 3 seconds that we're in the air. So my final y velocity is just going to be negative 10 meters per second. So in finding the magnitude, I'm going to do the square root of Vx squared plus Vy squared, which will be the square root of, so Vx that we found was, V naught x was 15. Actually, Vx and V naught x are the same. 15 and negative 10 meters per second squared. And so the magnitude of this velocity vector, or the speed of the object, is actually just going to be about 18 meters per second. So we're starting to see a trend with the way projectiles work. Typically, we will be finding some information related to time. Then we need to make sure we can use all different versions of our kinematics equations in order to solve for any unknown quantities. For question 3.21, a man stands on the roof of a 15-meter tall building and throws a rock with a speed of 30 meters per second at an angle of 33 degrees above the horizontal. So he's on a 15-meter tall building. So he's 15 meters above the ground. Here he is. He's got a rock. And he throws it with a speed of 30 meters per second, so a V naught of 30 meters per second, at an angle of 33 degrees above the horizontal. So we want to calculate the maximum height above the roof that the rock reaches. So first off, the rock makes some kind of path like this before hitting the ground. And we want to find the maximum height that it reaches. So like any other two-dimensional problem, I'm going to start by finding my components of initial velocity. So V naught x would be V naught times the cosine of 33 degrees, which would just be 30 times the cosine of 33 degrees. So V naught in the x direction is going to be 25.16 meters per second. Then in the y direction, we're going to have V naught times the sine of 33 degrees, which will just be 30 times the sine of 33. So in the y direction, our initial velocity is going to be 16.34 meters per second, approximately. So I am rounding a little bit here. And so I want to find the maximum height, and I want to do that by recognizing at the highest point, Vy is going to be 0. So I'm actually going to use the third kinematic equation for this situation. So I have Vy, I have V naught y. I also know Ay, which is negative g, or negative 10. And I want to find the highest point that it goes from the initial bit. So I'm actually looking for a delta y. So my third kinematic equation is, in the y direction, Vy squared equals V naught y squared plus 2Ay times my displacement in the y direction. And I'm going to solve this for delta y. So rearranging this will give me Vy squared minus V naught y squared all over 2a. And I can go ahead and simplify this a little bit by knowing that Vy at the highest point will be 0. So I'm ending up with just negative times V naught y squared, which is 16.34 squared, all over 2 times my acceleration of negative 10. So the highest that my object goes, or my ball goes, above the starting point on the roof is going to be just a simple 2.67 meters. I'm sorry, I made a mistake in my calculation. So that is not negative, or that is not 2.67 meters. That is actually 13.35 meters. Calculators are fun. So B says, calculate the speed of the rock just before it strikes the ground. So there's a couple ways to do this. I'm going to go ahead and remark that Vx is going to be equal to V naught x because acceleration in the x direction is 0. So I simply need to find Vy. So I can do this again by noting in my third kinematic equation that I know everything except for Vy. So I have V naught y, which is 16.34, positive. I have A, which is negative 10. And I have delta y, because the difference in height between where I start and where I end is actually going to be negative 15 meters. And it is negative because I'm starting at a positive 15 and I'm going down to 0. So my displacement is a negative 15. So starting with my third kinematic equation again, my Vy squared equals V naught y squared plus 2ay delta y. I don't need to do too much solving here because I have Vy squared already isolated. So all I need to do actually to solve this is to square root both sides and then end up with square root on the right side. So my y velocity at the end will be the square root of 16.34 squared plus 2 times negative 10 times my y displacement of negative 15. So the signs are very important here. Make sure you include all of them correctly. So I will have, when I plug this into my calculator, this is rather difficult to put in the calculator correctly. It appears. We end up with a final y velocity of, now this is the square root, so it's plus or minus 23.81 meters per second. So since there are two values, since we're inserting a square root value here, it is worth noting that we do not want the positive value. At the bottom of this motion, we really should have a negative Vy. So we're going to choose the negative value for this velocity. So what that means for us then is that in order to find the speed of the rock just before it strikes the ground, I'm going to go through trigonometry here and find the magnitude of this velocity vector. And that is going to be square root again of Vx squared plus Vy squared, which we can substitute in. Vx is going to be our V naught x, which was 25.16 squared. Our Vy we just found to be negative 23.81 squared. And so the magnitude and therefore speed of this object right before it hits the ground should be approximately 34.64 or 34.6 meters per second. So moving on, question C says the horizontal range from the base of the building to the point where the rock strikes the ground. So we don't have enough information in order to find to use the third kinematic equation for this. So we actually need to use the second kinematic equation, which is x equals x naught plus v naught x times t plus 1/2 ax t squared. Now the issue here is that in order to solve this and find our final x position, we actually need to find a value for time. So in order to find how long my object is in the air, I can go through the first kinematic equation for the y direction. So I know my final y velocity because I calculated it to be negative 23.81. So I can use the first kinematic equation to solve for time. So that is going to be time equals Vy minus V naught y over my y acceleration. So my Vy, which I found to be negative 23.81, minus my initial y velocity, which we found to be positive 16.34, over my y acceleration, which is just negative 10, gives me a time in the air of 4.015 seconds, which is approximately 4 seconds, so you could possibly round that. And then for the horizontal range, I just want to find this delta x, which is going to be v naught x times t, which for us, our v naught x was given to be 25.16, or found to be, meters per second, times our 4.015 seconds. So we end up with a horizontal range of about 101 meters. So calculations are finished. All that's remaining is to sketch graphs for the motion of this object. So let's start with an x of t graph. So this is our horizontal position. So we start at the origin and we move at a constant rate. And so 4 seconds later approximately, we should be 101 meters away from the origin. So there's my x direction. In the y direction, so I'm going to set my origin to be in the bottom left of my image here. So if I go back and look at my image really quickly, I'm going to set my origin to actually be down here. So the positive x direction goes from there, positive y direction here. So I do not start at an initial height of 0. I actually start 15 meters above the origin. So my y is going to start at the 15 meter mark. And I know that my highest altitude is going to be 13.35 meters from there. So somewhere over here, I'm going to be about 28 meters above the ground. Then, after 4 seconds, I'm going to hit the ground. So this actually occurs at some time to the left of the 2 second mark. So I should be a little more specific. It's somewhere to the left of the 2 second mark, because by symmetry, my graph should look something like this, just a nice parabola. And so my 2 second mark is somewhere over here. So this is somewhere to the left of the 2 second mark, because the ball has less distance to travel on its upward path compared to its downward path. Now I have a Vx of t graph. So because I've defined to the right to be positive, then this entire graph should just be a constant x value, or constant Vx value of 25.16 meters per second. I can just draw a nice horizontal line. This is 25.16, very specific, and that's meters per second. Then for the y velocity, I know it should have a negative slope of 9.8 or 10. And I'm going to start with an initial velocity of positive 16.34. So positive 16.34 is where I'll begin at time 0. Then, once I get to the end, I should be negative 23.18 after 4 seconds. And then I just need to connect these two dots. So we should, just like we agreed for this y position, have a peak somewhere to the left of the 2 second mark. And that's all there is to those graphs of motion.